In this video, I'll talk about geometric transformations. But first, I'd like you to watch this short video that'll demonstrate. Let's talk about reflections first. A reflection is an image or a shape as seen in a mirror. We could also say flip. Here's a reflection of a bird. Notice the bird looks the same, he's just facing another direction. Or the reflection of this amusement park in the water. Again, it's identical in the water as it is above. Here's a geometric representation of a triangle being reflected over the y-axis. And another of a triangle being reflected the other way over the y-axis. Here's a geometric reflection of the word mom over the x-axis. Here's a footprint reflected over a vertical line. The next transformation we'll talk about are rotations. A rotation is when an image that is turned about a fixed point remains the same, but's facing a different direction. We can also say spin. The spokes on a bicycle tire are rotated every time we move the tire. Here's a geometric representation of a triangle being rotated a certain amount of degrees about the x. Or these geometric shapes being rotated in a clockwise fashion. The head of a golf club on a golfer's swing is a rotation. And the way we move the parts of a Rubik's Cube are also a rotation. Here's a footprint being rotated or spun. Next, we'll talk about translations. A translation is an image or shape that's moved without a rotation or reflection. We could also say a slide. Here the dog is sliding across. Here a star is being slid across the page. Here the Martian is being slid forward and left and then back and left, as well as his footprint being slid down and to the right. And here's a geometric translation of a triangle. So let's get to our notes on geometric transformations. We'll start with reflections. This is a picture of a parallelogram being reflected over a vertical line. A reflection is a transformation in which a figure is flipped over a line. The shape does not change size. It just changes its location. The new shape is a mirror image of the original shape. The size and shape of the mirror image doesn't change. The line about which we reflect an image is called the line of reflection. I've been using that word image here. Let me define it for you. The image is the shape, in other words, the shape's coordinates, after the transformation or transformations have been made. So in the picture above, if the blue parallelogram is the original polygon, then the red parallelogram is the image. I also talked about the fact that the figure doesn't change shape. When you perform a transformation on a figure and the shape and size does not change, that is called an isometry. An isometry is when the transformation does not change the size of a figure at all. In the example that I just shown, a reflection is an isometry because the parallelogram is the same size and shape it was before the reflection. Let's look at an example. We're going to graph this image. In other words, we're going to look at the transformation, which is asking us to reflect it across the y-axis, and we're going to graph it in blue. First thing I'm going to do is graph each point individually. Since A is 1 unit to the right of the y-axis, I'll graph A prime, the new A, 1 unit to the left of the y-axis. So I'll graph each point individually, the other side of the y-axis, and then connect the points. Notice I've labeled them A prime, B prime, and C prime. Now we'll graph the triangle across the x-axis. Again, I'm going to graph each point individually. I'm labeling them A double prime, B double prime, and C double prime, and then connecting them so that they're differentiated from our blue triangle. Then I'll connect my vertices. The orange triangle represents the reflection of the original triangle across the x-axis. Now here comes the challenging part. Reflect the original triangle across the line y equals 3. So the first thing I'm going to do is draw a nice dark line at y equals 3. And now I'm going to reflect my original triangle in pink across that solid dark line y equals 3. First, let's look at point A. Point A is 2 units below that dark line that I wrote y equals 3 next to. So I will graph A triple prime 3 units above the line y equals 3. Watch. I'm going to call this point A triple prime to differentiate it from the blue and the orange triangle that we've already drawn. Now B is 1 unit above the dark line y equals 3. So I'm going to graph B triple prime 1 unit below the line y equals 3. Point C is also 2 units below the line y equals 3, so I'll graph C triple prime 2 units above. Now I have the 3 vertices for my triangle, and all I need to do is connect them. Sometimes this is difficult to do without patty paper, so I want you to watch a short video in which someone's going to demonstrate how to do the same type of thing with patty paper. Here, he's drawn the segment AB, and he's put a piece of patty paper on top of the segment he drew, and he's tracing the segment AB onto his patty paper. Watch carefully as he also places points at the top and bottom of the y-axis. His patty paper along the y-axis. I don't know if you noticed, but he put points on the top and bottom of his patty paper so he knew where to fold it. Now it fits directly on top of the y-axis. To reflect the segment over the y-axis, he'll simply fold his patty paper on the crease he's already made. Now he'll transfer the points A and B to A prime and B prime on the other side of the y-axis. Each time he's checking to make sure those points are in the location underneath his patty paper. He labels them A prime, B prime, and then connects them with a straight edge. The next transformation I'd like to talk about is rotation. Remember, a rotation is a spin or a turn of some figure or shape around a given point. That given point is called the center of rotation, and it acts like an anchor. If you look at the picture to the left, the blue trapezoid is being rotated some degree with an anchor at the bottom where the 2 dotted lines intersect. Where those 2 dotted lines intersect is the center of rotation. Once the rotation is completed, the pink trapezoid is the new image. So here's a demonstration on how to do rotations using patty paper. It really is the easiest way, and I really suggest that you use patty paper to do all of your rotations. So we start with this quadrilateral drawn in the second quadrant. Place your patty paper directly on top and make sure that it covers the X and Y axis, because not only are you going to trace the figure, you're going to draw a little X and Y axis directly on your patty paper, so that you can keep track of how many degrees you've rotated your figure. Now once I have my little X and Y axis on my patty paper, I'll trace the figure that I need to rotate. Make sure your tiny X and Y axis lines up with the X and Y axis underneath it on your graph paper. In this problem, I'm asked to rotate my figure 90 degrees. All rotations will be counterclockwise. Turning my paper so that the X in the middle rotates exactly 90 degrees while I hold my pencil at 0, 0 will give me the new location of my image. Now, I'll transpose my vertices from my patty paper to the graph paper underneath and label them with prime markings, little tick marks above each letter, to note that that is the new image and not the original figure. Once I have the vertices of my rotation, I'll connect them and make my parallelogram. So let's do one without using patty paper. It's much more difficult to do this way, but not impossible. Again, we are going to do all of our rotations about the origin, which means the origin is where I'm going to anchor my patty paper. Once again, all rotations will be counterclockwise. If I rotate 90 degrees about the origin counterclockwise, that completely turns the rectangle as we were shown before. Using the patty paper, A moves all the way around to that bottom corner. See above, and the rest of the vertices follow suit. Now let's talk about translations. Translations are another way of saying a slide. We will move our shape or slide our shape either right, left, up, or down, but we won't turn it. It'll keep its orientation and maintain its size. So a translation is also an isometry. Here's a way that we will write our translations. In parentheses, x plus 2, comma, y plus 7. The x plus 2 means that I'm going to move my original image 2 units to the right. The plus means positive, and the 2 is the number of units. The y plus 7 means that I'm also going to move it 7 units up. The positive comes from plus. X minus 9, comma, y minus 1 means that I'll move my original figure 9 units to the left and 1 unit down. Translate this figure. X plus 2, comma, y minus 3. The plus 2 next to the x means that I'm going to shift this entire figure 2 units to the right. The y minus 3 means I'm also going to shift it 3 units down. You really don't need to use patty paper for translations. We're simply going to move every point 2 units to the right and 3 units down, counting 2 right and 3 down from A, and 2 right and 3 down from B, etc., gives me the following vertices for my new image. Again, when you label your new image, make sure you use prime. Prime are the little tick marks that I've written on the top of each of my vertices. Our last step is to connect our vertices, following the pattern we see on our original figure. Our image should have the same size and shape as the original figure. It's just translated to a different location. Now let's talk about dilations. Another way to say it that we are dilating something is to say that we're resizing something. We're either enlarging it or reducing it, kind of like what happens to your pupils when you go in a very bright room or a very dark room. A dilation is a transformation that produces an image that is the same shape as the original, but it's a different size, like these two triangles. Their proportions remain intact. In other words, they're similar, but they're obviously not the same size. A dilation is not an isometry. One of the things we need to know before we perform a dilation is the scale factor. In other words, the amount of enlargement or the amount of reduction we're going to make on our original figure. If we enlarge our figure, the scale factor will be a number greater than 1. If we reduce the size of our original figure, then our scale factor will be a fraction, a proper fraction, where the numerator is smaller than the denominator. Scale factors are always positive numbers. In 8th grade, our center of dilation will always be from the origin. The center of dilation is a fixed point on the graph about which all the points are expanded or contracted. So in other words, we're using the origin and the distance from the origin to enlarge or reduce our figure. It seems a lot more complicated than it is. Let's look at this example. We're going to graph the image after the dilation of 3. So in other words, we're going to make this 3 times larger than it is. We're going to multiply every single one of the coordinates of our vertices by 3, starting with A. Then I'll multiply the coordinates of B by 3, graphing each one as I go and labeling them with prime markings, A prime, B prime, C prime, etc. Notice that this graph becomes so big it actually leaves my coordinate plane. So I've done my best to measure and estimate where these lower coordinates will be. As in my other transformations, I am marking all of my image vertices first, and then I will connect them in the end. When I'm finished drawing my image, it should have the same proportions as the original figure. It's just going to be larger. So if I actually did the ratio of the sides of my enlarged figure to the ratio of the sides of my small figure, all of those ratios would be the same. In other words, these two figures are similar. They're just not the same size. Remember, similar means that all sides have the same proportion.